NYU. So I thought a lot about what kind of proof I was going to do today because I do have a lot of favorites. I was thinking maybe John Nash's strategy stealing argument that hex has a dominant strategy for player 1, something about the harmonic series being divergent, or maybe even everybody's favorite identity, Euler's identity. But instead, I decided I would try something a little bit different. So this is a proof I came up with myself that's going to sound a little weird, but what I'm actually going to do today is extend the concept of parity from finite integers into transfinite cardinal numbers and use it to prove that a set with cardinality aleph null is actually odd. Okay, so what am I saying? Infinity is odd? That's nonsense. I'm a lunatic. Because we all know that these boring old number theory definitions couldn't possibly be applied to infinite numbers. Even is just 2 times n for some integer n. Odd is just 2n plus 1 for some integer n. Let's make new ones. So I don't really have time to go over the definition that I've constructed for even, but it's pretty easy to extrapolate. Right now I'm just going to talk about odd. And what I'm going to do is I'm going to use sets. So a number is odd if you can construct a set that has cardinality with that number. For example, for 5, we have this set that has A, B, C, D, and E, and then it obeys the following rules. 1, you can divide it into 3 disjoint subsets. 2, those 3 subsets union to make the original set. 3, one of the subsets is a singleton, and 4, there's a bijection between the other 2 subsets. As you can see, this will obviously translate normally into the integers, as in this example, where the singleton subset will be the +1 and the 2 bijective subsets will be the 2n. But let's see how it works with transfinite cardinals. Okay, so before we get to that, I just want to really quickly address the 2 exceptions that don't work with that process. 1, I'm just going to say odd by convention. Negative numbers, I'm just going to say they're odd if the absolute value is odd, and you can check that using the definition that I just stated. Now, let's get to checking the infinite numbers. So the setting question that I want to take a look at is the countably infinite set of integers z going from negative infinity to infinity. And I just want to quickly show you that it meets all the criteria that I just went over when redefining the concept of odd numbers. So we can break it up into 3 disjoint sets, being 0, the positive numbers, and the negatives. Obviously the union of these 3 is the original set. 0 is a singleton, it has cardinality 1, and there's a pretty clear bijection between the other 2 sets, the negative and positive numbers. That bijection being f of x equals negative x. If you want to check that that's injective and surjective, be my guest, but you might as well take my word for it. Obviously, you can try this process again with other sets that also have cardinality aleph null, and it won't necessarily work. But the idea behind kind of this extension of parity that I've come up with is that certain sets that might have the same size don't necessarily have the same shape.